So what is performance? You see, when I have a computer or when I have two people with a computer, there is always a question we need to ask ourselves. Whose computer is better? Is my computer better than yours? Or is your computer better than mine? Who has the best performing? Whose computer has the best or is the best? When we ask that question, it comes into two categories or more than one category, whereby how do we determine which computer is the best? The computers we have, which one is the best? Which one is the most optimal computer we have? And how do we determine which one is the best? We determine which one is the best by either comparing them for speed, who finishes something early, who does something more, who spends less time doing something. You know, those are the words we use when we want to test which one is better. So in this class, we are going to focus on a number of performance measures that are used to express or to assess computers. Now, a user of a particular computer can measure performance based on time it takes to execute a given job. So if I come to you and I tell you, oh, click on this application on your computer, the time it takes for the application to load fully and appear on your screen, to me, that is performance. To another person, he or she can say, okay, if I have a computer, then I will give it a list of things to do. And if it can do all of those things within the shortest possible time, then to me, that is the best computer. So when it comes to performance, a user can consider performance as the execution time. But an engineer can consider it as the throughput time, whereby it is measuring how many things it does, and not just how many things it does, how many things it can do within a specific time. So in this slide again, or in this class again, when we are talking about performance, we are going to be focusing on that. How do we build applications and compare them to know which one is better? Now, if I have to compare something, I am comparing it in a way whereby I am looking at a quantifiable way where I can judge. I can't just come and say my computer is better than yours. Under what criteria? Under what environment? It would be surprising to you to know that a particular computer can be good within a particular setting, but in another setting is a very, very bad computer. So what makes the computer better? What makes the computer great? What makes the computer so much so that I can confidently say my computer is better than yours? There must be a way I can quantify it. So we will look at the ways we can quantify performance. Before we look at the way we can quantify performance, let's have a chat about the instruction count. Now, in this course, there are going to be lots of abbreviations in this course. IC, instruction count, is one of them. So I would implore you to find a way where you can write these abbreviations and learn them so that in the later courses or in the later subjects we do, you would know what they are and you can follow along. The instruction count refers to the number of instructions executed by a CPU to complete a particular program or task. That is, if I provide the computer with a set of instructions and I load it up, the time it takes it to complete all of these instructions is what I'm calling the instruction count. The key points to note in instruction count. Instruction count is the sum of all operations that the CPU performs during the execution of a program. Different programs have different instruction counts depending on what task they are performing. Zoom user. The last time we came, I told you guys that whenever you are joining, make sure you join with your name and index number. I can see someone here called Zoom user. So I'm going to log the person off. So again, if I give the computer instruction, let's say I give the computer 2 instructions, add 2 numbers. That piece of code could be read in different ways based on who wrote it. So even if there's the same thing in which the computer is doing, because there are different programs, the instructions they may write may be different. So it is something we must keep in mind. If I tell the computer, okay, I'm going to test you based on the number of instructions in which you can perform, and I tell you to do the instruction of adding 2 numbers, and the way I wrote the algorithm is different for the 2. One has, let's say, 13 lines, another one has, let's say, 5 lines. Obviously, the 5 lines will run faster than the 13 lines. So again, we must keep in mind that the instruction count is different based on what it is doing and how it is written. The instruction count, when used in conjunction with other matrices like the CPI and the clock rate, helps in assessing the performance and efficiency of the CPU and the program.
So, this was the CPI.
Marvelous question. We will deal with that when we get here. So let's wait on that.
Okay, sir.
So as I said, we will have plenty of abbreviations, so keep note of them. So let's have an example of the instruction count. The instruction count, an example of it is what we have on our screen. So we have a program that would add 2 numbers and then multiply a 3rd number. So I have step 1, load number 1, or go and pick number 1. Then we go and load number 2. We add number 1 and number 2. Then we go and load number 3. We multiply the result of the addition of number 1 and number 2 by number 3, and we store the result. Which one of these lines here is the instruction count? That is my question to you. Based on everything I've said so far, which one of these here is the instruction count?
So, is it the storing of the results?
No, it is not.
Why the results of the addition by?
No, it is not. Let's go back here. Instruction count is the sum total of all operations that the CPU performs during the execution of a program. Let's come back here. Which one of these is the instruction count?
Add number 1 and number 2.
No, it is not.
But multiply the results of the addition by number 3.
No, it is not. Let's go back to the top here again. Instruction count is the sum of all operations that the CPU performs during the execution of a program. Let's come back here again. Which one of these is the instruction count?
Number 1 to number 5.
5.
Number 1 to number
5 or 6.
6. I think 6 because the 6 is also an
I
operation.
don't know if you are guessing or you are telling me. So which one?
Then number 1 to number 6.
It is number 1 to number 6. all of them together is the instruction count. That means that the time taken for the computer to do number 1, number 2, number 3, number 4, number 5, and number 6 together is the instruction count. Are we clear on that?
Yes, sir.
Now let's look at clock time. What is the clock time? We define the clock time as the time between two consecutive rising edges of a periodic clock signal. So over here, I have a rising. If I rises up to here and ends here and it gets up to here, then I have a, give me 1 second. Let me do this. Great. So that I can do this. Perfect. So if it rises from here to here, gets here, comes here, goes down here, and gets over here, then I have a clock time. Clock cycles allow counting unit computations because the storage of computation results is synchronized with the rising clock edges. Clock time required to execute a program by a computer is often expressed in terms of clock cycle. Now here, they are trying to tell you that if you are here, it means that the computer would rise, do the computation it has to do. When it gets here, by the time it gets here, it means another one should start. So whatever it is doing, it has to move that into the what? Memory. The second point, clock cycles allow counting of unit computations. Why does it allow that? Because the storage of the computation results. That means that if I was here and I did all of these things and I got to step 6 here, where I load the result and store it into the particular memory, or if I go and put it into display, for example, by the time I get here, I should be done. The computer should be done. So we use that to know, okay, this is how long you are performing a particular task. Now you should stop, the next one should continue. Now you should stop, the next one should continue. Because it is synchronized with the rising clock edges. Now, we denote the number of CPU clock cycles, that is, the time required to execute a job. For executing a job to be the clock count, CT. The clock time by CT, and the clock frequency by F is equal to 1 over CT. Therefore, the time taken by the CPU to execute a job can be expressed as CPU time is equal to CC times CT. This one here is on its own. We can also refer to it as CC over F. And that means that we are replacing CT here with 1 over F. Because over here, CT comes here and F comes down here. We've done change of subject. So now we have CT here, 1 over F here. I can replace CT by what? 1 over F. That is why I can either write it as CC times CT or CC over F. Now, it is very important that we know that the CT, the clock time, it is very, very, very difficult to get. The computer does its computations in nanoseconds. If you had to time it, it is very difficult for you to time it. But every computer runs at a certain frequency. Hence, the frequency, getting that is easy. That is why in times where you cannot get the clock time, or sorry, the cycle time, you can get the frequency of the computer to replace to calculate your CPU time. More so, it's, as I said, it may be easier to count the number of instructions in a given program as to counting the number of CPU clock cycles. And the reason why you are counting the number of CPU clock cycles so difficult is because of the CPU time. It's in nanoseconds. What watch are you going to use? Your hand, by the time your hand rises to press the stop, it has even done or gone over the time. Calculating it is very, very hard. Hence, we do not use CPU clock cycles to do most of the comparisons because it's very, very difficult for you to get the CPU clock cycles accurately. For me to say that, okay, my CPU runs at a clock cycle of, let's say, 2, your runs at a clock cycle of 3, hence mine is better. Getting the information on the CPU clock cycles is very, very hard. Therefore, we use the clock cycles per instruction as an alternative to CPU clock cycles. And again, this is where we see the CPI, clock cycles per instruction, CPI. Now, this is how we calculate the CPI. CPI is equal to the CPU clock cycles of the program all over the instruction count. In cases where you don't have the CPU clock cycles of the program, then we can say that CPU is equal to the instruction count times the CPI times the clock cycle time. Or we can say the instruction count times the CPI all over the clock rate. So these are formulas we can use to calculate the CPI and the CPU time. Are there any questions?
So would we get examples so that we see how it works?
Of course, the class has not finished, so there are examples. Or do you like drinking soup before the fufu comes or something like that?
No, sir.
It's like every time you want to drink the soup before the fufu comes. Wait, it will come, okay?
Okay, sir.
But before you eat the fufu and the soup, you must know the formula. And this goes to this, that most people, me, for example, if there's anything that has to do with maths, I like it more than anything because it is easy for me to read and it is easy for me to comprehend. But one thing you get to know when you are teaching various students is that students find maths difficult. The difficulty is not in the expression of the maths, because if you laid everything out, they could write the maths. The difficulty is in deriving the formula for them to put everything in. The way in which most people go at it is by chewing the formula. The problem is that you can't chew to your die. There comes a point in time in your life whereby you have to try and understand the maths. Especially those of you who want to go into high-level programming or high-level understanding of situations or high-level algorithm or high-level system architecture or high-level analysis, there would be maths. There is nothing in this world that is worthwhile doing that doesn't have maths. So I get it. Everybody's afraid of maths. They see maths formulas up and down. You are afraid, okay, it's maths. Oh my God, it's difficult. All of that is there. But there's another truth. There comes an age where you have to sit down. There is no running away. There's no looking back. You have to learn it. And in learning it, in my experience, you must know the formula, how the formula works, how the formula comes together. So again, if I want you to calculate the CPI, which is a ratio, It is the CPU clock cycles for the program over the instruction count. If I ask you to calculate the CPU time, then it is either the instruction count times the CPI times the CPU clock cycle time, or the instruction count times the CPI all over the clock rate. That is, if you have the clock rate, then you divide it over. If you have the clock cycle time, then you multiply it with the ones at the top, depending on the information you get, depending on the way the question flows. We must understand this. And the reason why we must understand this is that we are going to implement it, like how Mr. Sua wants an example. So how do we implement it? It is known that instruction set of a given computer consists of a number of instruction categories. Everything in which we have been saying, we have been acting as if the computer is only going to do one thing, and when it is done, it will stop. It does not happen like that. It may be doing 1,000 things at a time. So it may be doing some ALU assignments. It may be loading things to and from to memory, or to a particular IO. It may be importing or bringing things in, or it may be storing them, or it may be branching to do some other things whilst it's waiting for some other information and so on. So in that case, or in the case that that is going on, the CPI for each instruction category is known as the overall CPI. That is, I am going to give the computer a list of things to do. I would watch it do all of them and tell me, okay, all the things in which you did, what is the average CPI of all of them? Now, to do this, we are going to multiply the CPI times the times in which it occurs. What does that mean? So if I take this half of the formula, CPI times I, that alone, I have a table over here. It tells me that this is the instruction category. So ALU, load and store, branch, and others. Now for ALU, the percentage of occurrence in the CPU was 38. And it did this once. So for each of the 38% times in which it happened, it was done once. The number of instruction cycles. So one cycle, then it is done. For the load and store, it took 3 cycles before it was done, and it occurred around 15% of the time. For branching, it occurred 42% of the time, and the number of cycles that were needed to do branching were 4. For others, we have 5 here, and then the number of cycles we used was what, 5. Now, if we are taking this half of the question, CPI times I, forget about everything else, CPI times I, that alone, it means that we need to come in here. I'm in Excel now, right? So I'm here. Let me zoom in a bit, open it up a bit. For that half alone, just that half, it says that I must take the CPI, so I must go and take the CPI and multiply it by the number of occurrences, which is number of cycles in which it spends, number of cycles per instruction, which is denoted by what? I. So for our question, when we come back here, it says that the CPI is 23. It's 38. So again, back here, I have 38 times the cycles per instruction which occurred, which is what? 1. So here I have 38 times what? 1. Now, this piece of thing which I've done here, if you watch the formula here, this half is taken care of. CPI times I, that is taken care of. But we have the summation symbol here, which says that from our starting point to our ending point, we should add every CPI times I we find. That means if I go back to this table, the next CPI I find is 15 and 3. And for the formula, I'm going to say, when you are done multiplying this together, go and add the multiplication of 15 times what? 3. Then go and add the multiplication of 42 times 4. Then go and add the multiplication of 5 times 5. So all this formula is telling you is look for the CPI, which will be given, of each of the instruction categories, multiply it by the number of cycle instructions, then add them all together. So that is the top half of the equation. That is the top half of the equation. The bottom half of the equation is how many or what was the instruction count you were looking at. So if I come back here, I'm looking at 38 plus 15 plus 24, 42 plus 5. So back to my Excel again. I am looking at 38 plus 15 plus 42 plus 5. This will give me the total instruction count that I used in my CPU. So over here, if I do this, it would give me an answer. Over here, if I do this, it will give me an answer of 100. Then, according to the formula again, I am supposed to take whatever that is here at the top and divide it by whatever I have at the bottom. And whatever answer I get is my overall CPI. As you can see, that is what I get.
So does it have a unit?
No. It's a ratio, so no unit.
Okay.
One second, please.
Okay, sir.
Okay. Now, there are some things we should be noted from us. Number one, it should be noted that the CPI reflects the organization and the instruction set architecture of the processor, whilst the instruction count reflects the instruction set architecture and the compiler technology used. Hence, the CPI or the overall CPI will give us a fair idea of the performance of the computer. So this shows that the degree of interdependence between the two performance parameters, therefore, it is imperative that both the CPI and the instruction count are considered in assessing the merits of a given computer or equivalent in comparing the performance of two machines. Now, with this in mind, what is MIPS? MIPS stands for million instructions per second. And it is the measure of instruction executed. It is a measure of the instruction executing rate of the CPU. It indicates how many millions of instructions a CPU can execute in 1 second. How do we calculate MIPS? We calculate MIPS by dividing the instruction count over the execution time times 100 raised times 10 raised to the power 6. Note, 10 raised to the power 6 gives you a million, hence the million instructions per second. Over here, I have a computer B. I'm assuming this computer over here is computer A. Here I have a computer here called computer B. I want you to calculate using this formula we have over here. That is CPI times I over instruction count. And tell me, what will be the overall CPI of this machine I have here, machine B? When I come, I will call you people at random to tell me what you got and how you got it. I'll give you guys 2 minutes to do the calculation and tell me the answer. And do the answer. Is that clear?
Yes, sir.
Your time starts now. Dennis, what answer did you get?
Sir, can you please see the formula for the millions?
Have you all written this one down?
Yes.
So this is the formula for the MIPS, that's the millions instructions per second. By the way, when I ask you guys to answer something, because you're not in class, I take record of each mark. So those of you who do not have a name, an index number associated with your name, it means that the mark, you get it, but I don't record it because your index number is not there. So let's take note of that. And secondly, if I call you, answer a question and you don't respond, I give you a -2. I expect that whenever the class is going on, you're not in a car or something, you are in a place where you can have the class. The fact that it's online doesn't mean you should be doing something and then having the class. So let's have that point clear. And this is the formula for the CPI. This is the formula for the CPI. The overall CPI. So again, you are calculating the overall CPI for this, and you're also calculating the MIPS for this. But before we talk about the MIPS, what is the CPI for machine B? Dennis.
Sir, please, I'm still on it. So
Hey, move here.
The formula for the CPI again.
Let me leave it here. Okay, so can we start getting answers now?
Yes, sir.
Rudolph, what did you get?
Sir, please, I'm still on it.
Hey! David, what did you get? David Nudi.
David, I'm getting 3.26.
David, are you sure of your answer?
Let me just go through. Just a quick one.
Jennifer, what did you get?
$9.09.
9.09. Hey, Jennifer, your own is too high.
Ish.
Emmanuel, what did you get? So this is the calculation for it. Right? So this is the calculation for machine A, the MIPS and the CPU average, but let's put that one aside. This is machine B. So machine B, we are looking at 10 times 1. Over here, we have 10 times 1. Then we have... Oh, no,
No,
sorry.
that wasn't the question you gave us.
Yes, that wasn't the question I gave you. Sorry. That one is over here. Good.
Yes.
So for machine A, we have... Machine B, we have 35 times 1. So over here, we have 35 times 1. Then we have 30 times 2. So we have 30 times 2 here. Then we have 15 times 3. So we have, I think, 15 times 3 here. Then we have 20 times 5. So we have 20 times 5 here. So all of this over there should give us 2.4. So if the answer is not 2.4, then we have a problem. So Jennifer, how did you get 9? Tell us. Please note that if you're using the computer, BODMAS rules apply. So make sure you write it in a way whereby it knows that it is multiplying the two numbers. Then when it is done, it will go and add.
Yeah.
Are we clear on that? How many of you got the 2.4?
So please, you are not hearing. I'm not hearing.
Same here. Yes, please.
Can you hear
your
me?
network?
Can you
Yeah,
hear
can
me?
hear
Still going back and forth.
Yeah. Now it's okay.
Now it's okay. I'm saying that you're supposed to multiply each of them together and add the next one. So when you're using your calculator, use it in such a way whereby you can multiply them together and add them together so that your computer knows that BODMAS rules apply. When you are done, you're supposed to get 2.4. The question here is, which one of you here got 2.4?
I do.
So we have just one person getting 2.4.
Yes.
Please, I think I didn't. The instruction count. Can you please help me? Maybe I forgot, but I used a different number. So
What number did you use for the instruction count? And how did you get your instruction count?
please, can you go back to the table?
Okay, so this is the table, right? And the instruction count is 35 plus 30 plus 15 plus 20. So what did you do?
I added them. I didn't use the 100.
But that's why I said 35 plus 30 plus 15 plus 20. If you add them, you get 100. What did you get?
Oh, I got 7. I don't know, but I wrote 73.
Are you sure you added them well?
But yes, that was the idea. But I don't know why I wrote. I don't know whether it was because I was in a hurry or something, or maybe it was the pressure. But the idea was to add them. I don't know why I wrote 73.
Hey, there was pressure involved. I'm sorry.
No, I just wanted to give you the correct answer when you call me. That's why.
I see. Now the MIPS for the first one, it is the clock rate over the CPA times 100 raised to the power 6. The clock rate has been given here as the top as 200 megahertz. The mega there stands for 1,000,000 hertz. So it is 10 raised to the power 6. So we have 200 times 10 raised to the power 6. That is 200 megahertz all over 2.76 times 100 times 10 raised to the power 6 again, because the formula says we should take the CPI and multiply it by what? 1,000,000. In that case, the two of these will cancel out and I'll be left with 70.24 as my MIPS for machine A. For machine B, I have my clock rate, which is still going to be 200 times 100 raised to the power times 10. Why did people say 100? Times 10 raised to the power 6. All over 2.4. That is the 2.4 we calculated here, times 10 raised to the power 6. And this should give me 83.67. The question is, and here's the question. Which machine is better if I'm looking at them through the eyes of CPA? Is it machine A or machine B? Which machine is better? Is it machine A or machine B? Based on the values we got here, which one is better?
Machine B.
Machine B.
Looking at this again, if I'm taking the MIPS, which machine is better? Machine A or machine B?
Machine B.
Machine B is better than machine A. Why is machine B better than machine A in terms of MIPS?
So it can perform more instructions more instructions per million.
Per million. Very good. Are we okay? Let us note something here. That in your exam, let's say all of this thing here was 5 marks, right? You will get, let's say, 2 marks for solving all of these things here. That 3 marks is for you to tell me that MIPS of B is bigger than MIPS of A, and the reason why it is big, that one will give you the highest score. Because remember, our job is not to calculate the mass. The mass is there to tell us something very important. Which computer is better? So if you solve it all and you don't tell us which computer is better, then why did you go bother solving it in the first place? Now, in the day class, someone asked a very sensible question. What if I skip the questions and just tell you which one is better? Now, we need to know how you derived at that conclusion. So it means if you don't have arguments and you derive at the conclusion, we'll give you 0 because we don't know how you derive that conclusion. It must be backed by facts and figures. Are we clear on that?
Sir, your microphone.
Your mic.
My microphone went again. Hey, this is my microphone there. Where did it stop?
Where you were stating where we should which one is better, we should state it.
Good. So I'm saying that for every question you're given based on performance, at the end of the question, you must state which machine is better and why. After you have performed the calculations you need to calculate. If you don't state which machine is better, you will lose marks for that. And I must be very clear on that. Because again, we are learning not just to know forward, we're also learning for exam. So anything that has to do with exam, I'll give you a note. And the note here is, if we are calculating performance, MIPS, clock time, instruction count, or CPI, any of these things in which we are going to be calculating for, you need to tell us which computer is better and why you think that computer is better based on the calculations in which you did. With that in mind, over here I have machine A and machine B. I want you to calculate both the overall CPI and the MIPS of machine A and machine B. I'll give you guys 2 minutes to do that.
So are we using the 200 megahertz?
We are using the 200 megahertz for the MIPS, yes. Now, if you didn't know that you have to ask that question if you are using the 200 megahertz, it means that what we are doing, you don't understand. So think of it. So I'm going to be starting to ask for answers very soon. Ladies first, so we'll start from Jennifer.
Please, I'm not done.
I didn't call you. I just said we'll start from you. Hey,
Oh, okay.
Jennifer.
Okay.
Okay, so time's up. We need your answers now. Mark Adai, what do you get? Yeah, Dennis.
Sir, the A, I had 500 MPS, and the second one I have 4.78 MPS. The B,
500 MPS.
yes,
MIPS.
yes, please.
Are you sure? For the A, what was the CPI you get?
It was 0.4.
Hey, are you sure? You multiplied 8 times 1 plus 4 times 3 plus 4 times 3 plus 2 times 4 divided by 8 plus 8 plus 8 plus 2. And you got what?
Okay, I didn't add the 100. Sorry.
Even if you don't add 100, because these two cancel out, even if you don't add that, this one over this one should give you 2.22.
Yes.
So what did you do? Because, yeah, what did you do? Jennifer, what did you get? Is Jennifer there?
So please, I'm here.
What did you get for the MIPS of A?
So please, I'm
Samuel,
what
what
I
did you
have
get? What you had was what?
wrong. I didn't add the 8 plus 4 plus 4 plus 8 plus 4 plus 4 2 plus 4.
Then what did you put as the denominator? 100?
Yes, please.
It's not always going to be 100. Remember, it is the total number of instructions in which you used. So here it is 8, 4, 2, and 4. Are you okay? So that is what is going to give you the total instructions. This for machine B, it is 10, 8, 2, and 4. Yes.
Okay.
So you mentioned my name.
Yes. What did you get for the CPI of machine A?
2.2.
Are you sure? Okay, okay. What did you get for machine B?
1.9.
Okay. So for machine B, Mark is telling us that he got 1.9, and he's right. It's supposed to be 1.9. Well, actually 1.92. Normally you 2 decimal places behind. You get 1.9. Yes. What did you get for the MIPS of machine B?
105.26.
So over here, I got 104.17. And the reason why I got 101.17 is because of the decimal points I'm assuming. So check the decimal points. Are we okay?
Okay.
So again, if you are looking at the CPI, which computer is better? Is it computer B or computer A? Computer A is 2.2. Computer B is 1.92. Which one is better?
Computer B.
Computer B is better. Are we all clear on that?
Yes, sir.
So the example shows that although computer
Hello,
B,
sir.
yeah,
Hello, sir. So, if I understand you well, it's not always that it's going to be 100, but rather we are going to use we are using a total what's the name of it? We are using the
fraction count,
yes, please. This is where I got lost. So
total number of
I did,
instructions.
so I used it. My denominator was 100. So that's why I was arriving at 500, like Dennis. So so I just noticed that it's not always going to be 100. It's depending on the sum
Over
of.
here, it was 100 because they said the percentage of occurrence. And of course,
Okay,
the percentage, the total is always going to be 100. Over here, they didn't say the percentage. And even over here, if I add all of these things up over here, I should get what? 100, right? But when
Yes,
I'm
sir.
here, the total instruction count is 8 plus 4 plus 2 plus 4. Remember, it says number of instructions in millions. That is why over here, the times 10 raised to the power 6 is added to the CPI of machine A and machine B. But of course, they'll cancel themselves out. Do you understand? So
Yes.
you must read and see what they are given in. As I told you before, math is about structure. And math is mainly, the difficulty in math is people fail to follow structure. Once you know the structure, then you can implement the structure. So we must learn the structure, then we would implement it. Is that clear?
Yeah. Okay.
And when you are done with everything, don't forget, you must state why one is bigger than the other or one is better than the other based on the facts in which you had what you have. Are there any questions?
Okay.
Are there any questions on what we did?
Sir, based on the answers, so I got your answer. I got the right answer, but I want to be sure about this. When the MIPS, let's say for A, which I got 90 points, I got 90.90, and for the MIPS B, I got 104.71. Based on that, you can tell that the MIPS B is better than the or faster than the MIPS A. But it seems you were doing some calculation, the CPU. Does that mean that it will always tally? That the CPU B is better than the CPU A? Would you always tally with the MIPS A and MIPS B and A?
It may not always tally.
Okay.
So it may not always tally. That is why all of these matrices are taken into consideration. You can see that in the slide at various points, they tell you that as a performance, it is interesting to note here that MIPS has been used as a performance measure for machines. One has to be careful in using it to compare different machines having different instruction sets. You can note that in both of them, if it is 100, both of them are 100. If one is 100 and one is 120, the results you are getting is poor. The reason why you need to make sure that the instructions for both are equal is because MIPS does not track execution time. So if I am comparing and execution time is different, I'll get different values. So we use these, you can see that over here as a note, I put it there empirically that when you are assessing, it is very important you know that it depends on the CPI and the instruction count. They depend on it. Hence, it gives you a particular picture. If it is not there, then you use another method to compare. So based on the things you have available, it will give you a particular answer that will give you what you need to do based on the variables you have. So you need to take note of some of these things.
Okay.
I
didn't realize one was performance and one was instruction set.
So the last thing we'll discuss today before we close is Amdahl's law. We'll discuss it when we come next week, then we'll do calculations on it. What is Amdahl's law? And how does Amdahl's law play a role in the things we do? Now, if I was to ask you guys, for example, if I had a 32, if let's say I had a 2 gig computer, the computer I have is 2 gig, right? And for some reason, I go and buy 4 gig or an additional 2 gig so that now my computer is 4 gig instead of 2 gig of memory. Will my computer be better or not?
It will be better. Okay.
How better? Let's use 1x, 2x, 0.5x. How better will it be? That is 0.5 times better, 1 time better, 2 times better. How better will it be?
Please, can you state the figures of the RAM to you?
So let's say if it will be 2 times better or half better, or how better will it be?
I meant the storage sizes, or was it RAM?
2 gig, 4 gig.
2
times better.
2 times better.
It will be 2 times better. Okay. If I change it from 4 gig to 8 gig, how better will it
be? 2 times better.
If I change it from 8 gig to 16 gig, how better will it be?
So I think there would have to be a rate
Well, I'm asking, according to you, 2 times
I
better.
understand, but I'm trying to say there
Well,
has to be.
according to you, Yancho, when you're Ghanaian politician, we are met you, 2 times better.
2 times better.
2 times better.
Sir, are you
Any
comparing
other?
it to the? Sorry.
Mhm.
Are you comparing it to the 8 gig? Are you comparing it to when it was 2 gig or to when it was 4 gig?
No, at this point in time, my computer is 8 gig and I put in 16 gig. How better will it be?
Okay, me too. I'm with listen. I think it will be 2 times.
Okay. Now, if from 16 gig to 32 gig, how better will it be?
2 times better.
2 times better. Okay, all right. Now, the way you are all saying 2 times better, 2 times better, I know. According to Amdahl's law, that is not possible. You see, technically, it will not be 2 times better. And that is what we all think. That if I just have a computer that is 8 gig and I put 16 gig inside it, because now there are 2 8 gigs, my computer will work 2 times better than it usually does. It is not true. Because your computer will not be doing the same thing which it is doing. It will not go and bring in additional power. The power would not change. That's not going to happen. The more you add performance, it comes to a point in time in your computer that the performance you are adding will taper off. That is, if I have a computer that is 32 gig and I go and put in 64 gig in it, my computer is not going to be 2 times better than it was when it was 32 gig. It wouldn't work like that. There comes a point in time where your performance will just follow up. For example, if I had a computer that was 8 gig and the only thing I did with the computer was use Word, was to type letters, and I go and buy a 32 gig and put it in that same computer, and I'm still typing Word, the computer will not perform better because I'm using a 32 gig, because the word processing doesn't need that much processing power to do. So I may not even see any gain in what I'm doing. What I'm saying doesn't make sense.
Yes.
So
Yes.
are you saying that if someone is using, let's say, a laptop with 2 gig RAM and using it for web browsing, and another person with has maybe a memory of about 8 gig RAM and is also using the same web browser, it doesn't matter. Like, are we saying that the
that's not
performance
what I'm
doesn't
saying.
matter?
That's not what I'm saying.
Okay. All right.
Okay, that is not what I'm saying. Now, this is what I am saying. I am saying that if you had a computer that had a 2 gig RAM in it, okay, your computer had 2 gig RAM in it, and you went and took that computer and changed it from 2 gig to 4 gig, obviously there would be a 2x increment. If I take that same computer and I took it from 2 gig to the 4 gig that it is now, and took it to 8 gig, that same computer, there would be an increase in productivity. Again, let's say it will be 2x. But from the 8 gig to 16 gig, there will not be a 2x increase. From the 16 gig to 32 gig, there will not be a 2x increment. There will probably a 1.5 or a 1 or a 0.5 increment. But the double increment you think you will get because you double the amount of memory capacity, you will not get that. Because the needs of the computer, at some point in time, his needs will be met, and the computer itself cannot perform better than its needs. So it will taper off. Do we understand? So if I am looking at the graph in which I have over here, I'm looking at the situation whereby when there is improvement, let's take the green line, right? When there is improvement, the computer will improve. You can see that the computer is speeding up based on the number of processors. It's speeding up. It is speeding up. Now, when it gets to a certain point, it can't speed up more than it has, because that's why I gave you the example of the Word. Let's say the computer that was 2 gig, I was using it just for Word. If I put 4 gig in, I will see improvement. I'll see the typing has improved. 8 gig, the typing has improved. 16 gig, the typing has improved. But it will not be as fast as what it was when it was from 2 gig to 4 gig. Because the computer doesn't need the additional memory that you have added for anything. Because the Word will take at tops, let's say 4 gig. After that, it doesn't need anything anymore. So even if I add 128 gig to my computer, the Word will still take its 4 gig. And if it is met, the rest is useless. So there comes a point in time in the computer whereby you adding additional improvements, be it memory, be it processor, be it bus lines, whatever you want to add, it becomes useless because the computer at that point in time will not add any additional speed up. It will not improve. So Amdahl's law asks a question to us that at what point in time is adding improvement useless? At what point in time is the improvement you are adding not going to work? And if I add something to the computer in terms of improvement, by how much will the computer improve? As I said, with performance, we deal with the quantifiable. That means that if we can't quantify it, we can't use it. It has to be quantifiable. So if I'm saying I'm moving from 2 gig to 4 gig, by how much growth will the 2 gig to 4 gig give me? By how much growth will the 4 gig to 8 gig give me? There must be a figure. And that figure there would be given up by the speed up. And when we arrive here next week, our job is to take Amdahl's law, learn speed up. How do we calculate speed up? How do we calculate speed up when we have enhancement and performance, or when we have the time? So we'll calculate speed up when we have the performance and when we have execution time. And the speed up will tell us by the improvement, by how much. So you would see that we can also calculate the improvement of the computer based on a particular fraction. For example, if I leave the computer how it is and I change just a particular part of it, how will my computer improve? We'll use this formula here to calculate the improvement we will get. And we'll try some questions and know the percentage of improvement that we will get over the original computer. And we will see that it is not always that if I take something from 16 to 32 or 32 to 48, I have doubled it, but it will not give me double the word improvement. So once I know the improvement, I need to go and compare the improvement I have with the money I'm going to spend and ask myself, will it benefit my company? Will it benefit me? Will it benefit the job I'm going to do? So when we arrive here next week, we are going to start off our class by learning Amdahl's law. And when we are done, we are going to learn memory. What is memory? How does memory work? What are the memory systems we have? And so on and so forth.
Thank you, sir.
Are there any more questions for us? As always, the video would be made available to you after the class, and the notes will also be made available to you after the class. Remember, the assignment in which we did is your assignment 1. So I'll record the marks into what you are doing. You're left with assignment 2, your mid-semester, and your group project work to do. And I will score all of them and add them to your exam mark and give you overall score. Everything you do is being scored. Every single thing. Like today, the questions I asked you, Jennifer, answer. This Dennis, answer. Every answer you give, I'm scoring it. And if your next number is not where your name is, you get the score, but I'll give it to God because you don't want it, because your index number is not there. So I've donated Jennifer's mark, Dennis's mark, all of I've donated. Dennis, I've donated it to the Lord. Dennis, your index number is there, so you have your own. But Jennifer, David, somebody I made rabbit. Yet I was saying somebody a collection and they're Sunday. Anyway, if there are no questions, I would like you guys to enjoy your weekend. And we'll meet here again next week. The time has changed, so we're meeting at 3. So when it is 3, we'll have our class.
Okay, thank you.
Hey.